Hey folks, got a new idea with electric potential, and that involves the electric potential created by point charges. And I've rewritten two of the equations that we've been discussing. What is change in voltage and what is change in potential energy if you have a change in voltage. So the electric fields that we've been dealing with so far, so for instance, in the previous example, well, these were constant electric fields, right? Every field I've drawn is constant, okay? Well, in this example, we're going to have a field that varies over distance. And the very simple example is, let's say I have a positive charge, and I asked you to draw the electric field created by that positive charge. Well, that field would move outward, or not move outward, but it would radiate outward like so, right? Okay, that would be your electric field. And that electric field, you'll recall, is kq over r squared in the r hat direction. If q is positive, the field points outward away from the charge, and if the q is negative, the field is negative, meaning it points radially inward toward the charge. Also, recall what that field is based, the direction of that field is based on. It's based on what would happen if I put another positive little test charge in this region. So for instance, if I put a little positive test charge here, right there, a little positive Q, well, the other guy will push him away. So that's a radially outward direction, okay? Well, what about change in voltage here? Okay, so let's go from A to B. Now, we are going against the electric field, okay? So if I look at my change in voltage equation, if I do my dot product, that should be negative, and then I've got a negative out front, so my delta V should be positive. So whatever answer I get here, it better be a positive answer. Also, again, think about it as electric potential is like electric height, and we are going uphill from A to B. We're going against the field, so we're going uphill. All right, well, we're just going to use this equation along with this equation for electric field, and we're going to put limits from A to B in. So if we do this, change in voltage for a point charge is negative the integral of E, which is kq over r squared, dot, and instead of saying dr, we're going to say or instead of saying ds, we're going to say dr because we're moving radially inward or outward here, okay? Now, you'll notice that we are moving this way. We're moving to the left. So this is actually a negative dr. Or another way to think of this is this, okay, is going to be, there's going to be two negatives in here. The dr itself is negative because, in other words, a positive dr would be outward, so a negative dr is inward. And we're dot producting the electric field, which points to the right, with this negative dr. So when I dot product those two things, that involves another negative. So what you're going to see here is, just looking at sign now, you get negative the integral of, there's a negative here, and this dot product is a negative. So you got two negatives there, which means inside the integral you end up with a positive. So you just have kq over r squared dr, okay? And then we're going to go ahead and pull out anything that's constant. So change in voltage is negative. Well, k is constant, as q is constant, and we're going to integrate from A to B dr over r squared, which is the same thing as r to the negative 2 dr. Okay, so now we're going to use our power rule. So you get negative kq. This becomes r. You add 1 to the exponent, so negative 1 divided by negative 1. Okay, so we have yet another negative in here, and you're going to evaluate that from A to B. So that simplifies down to kq over r, evaluated from A to B. And so your change in voltage is, for a point charge, is kq over B minus kq over A. Now, let's think about this for a second. Is that positive? Well, B is smaller than A. So 1 over B is bigger than 1 over a. So when you subtract these two, you will indeed get a positive value. So as we did conceptually, we knew we should get a positive value here. And we did get one. Now, by the way, if you didn't get one, you just forgot a negative somewhere. There's a lot of easy ways to forget a negative. So just add negative in there and you'll get it right. All right. Now, some things to notice about this equation. Where is voltage 0? Okay, where is this 0? Well, if I make A infinity, as A approaches infinity, the voltage at A would approach 0, right? If I make A infinity here, something over infinity is roughly 0, okay? So we define 0 voltage at infinity, which means the absolute voltage at any point is simply KQ divided by where you're at, R. So like in our example, it'd be KQ over B. If I started at A equals infinity, the voltage at B would just be KQ over B. So this is actually the equation that we're going to use from here on in to determine the voltage created by a point charge. It's just KQ over R. Now notice it's not a vector, it's a scalar. It's just a number, okay? It's how big. Something else I'll mention here is, like in the previous video, we talked about equipotential surfaces. So in this case, they would be concentric circles. An equipotential surface is perpendicular to the electric field at all points, and that means the voltage is the same at all points along that equipotential surface. Now I'll label that. That's an EQUI, potential surface. And actually, it'd be a sphere surrounding the charge. And then you have, and the next one would be, you can have an infinite number of them, obviously, but there'd be the next one, etc. Okay, so they are perpendicular to the field at all points, and they have the same voltage at all points. It'd be KQ over R, whatever that value is. All right, now one last thing I'll mention about, I'll actually kind of cover the new equation. What if we had a second charge? And here he is. Here he is right there. And let's call him little q. And we're going to start with him really, really far away. So he's really far away. And we're going to push him to B. Now, he doesn't want to go to B, right? He's being repelled by the other q, this q over here. He's being repelled. So we have to push him to B. So he's gaining potential energy. And by the way, at any point, like let's say he's here, if I let him go, he's going to fly out to the right. So we're lifting him up is another way to think of it. So if we lift little q all the way from infinity to B, how much work will that take us? Or how much potential energy will he add? So our change in potential energy would be his charge times this voltage, which would be KQ over R. Now, just for fun, I'll write minus KQ over infinity if we're starting at infinity, which that's just, that whole thing is just 0. And so you get the potential energy of that two-charge system is K big Q little q over R. Now, that's true for the potential energy of any two charges. Now, if you look at that equation and you think about it, that form of equation should look familiar to you. You might recall in first semester that gravitational potential energy was negative GMM over R. Now, in that case, it's negative because masses always attract each other, whereas in this case, we have two like charges that are repelling each other, so that's why the sign is different. But the form of the equation is the same. You have a constant out front. Instead of big G, it's K. Instead of two masses, well, now you have two charges, and we divide it by R again. So if you have 2 point charges and you're trying to find the potential energy of the two of them combined, it's just this. Another note on this equation, if the charges are opposite sign, this is negative. In other words, if this little dude here was negative, well, he would fall toward B. He would lose potential energy. His potential energy would be 0 at infinity, and he would lose potential energy as he fell toward B. Whereas a little positive charge, he starts with 0 potential energy at infinity, but we have to push him to B, so he's gaining potential energy as we move him to B. So again, you have to worry about what the change in voltage would be the same in both cases. And we'll do a few examples of that in the next video. But the change in potential energy would be different depending on the sign of the charge and what they want to do. All right, I hope that video was helpful. In the next one, we will do some numerical examples with some distributions of charge with different point charges in and around different places. And you get your calculators out for those. All right, have a good one.